You wait for like minutes. I'm hearing in your Zoom. Good. Okay. I would wait 2 more minutes maybe just to see if people come. Yeah. Thank you, Alana. Yeah, I mean I can fit in time. So we should go. Oh.
Hi, everyone, and welcome to our Spring Wednesday at NICO series. Appreciate seeing so many familiar faces in person. Thank you so much for taking your time to join us. Welcome also to our online participants. We encourage you to be active participants in today's discussion as well. Please drop any questions into the Q&A at the bottom of your screen. We will have, for those that are in person, we are still abiding by university policy recommendations that we not serve food in these forums. We hope to get back to our time-honored tradition soon, but as of today, we will not be serving food, but we will have some cookies for you to pick up on your way out. Thank you for joining us. One announcement, we are still looking for some students and scholars to, please come on in, some students and scholars to join our lightning talks. So if you would like to share some of your exciting research or practice those presentation skills, please go and submit your name on the website under NICO events. You'll see a link for lightning talks. And for those online, Emily will put that link in the chat for today for online participants. With that, I would like to welcome a very familiar face here at Chambers Hall. Sourav Medya is a research assistant professor at the Kellogg School of Management. He gets the prize for the shortest commute of our speakers this quarter and prior quarter too. He'll be talking to us about optimization and learning on graphs. Please join me in welcoming Sourav.
Can you hear me well? Okay. Yeah. So welcome everyone. There are so many good speakers, and at least I beat them by something, by taking the shortest to work. And so yeah, I'm talking about optimization and learning on graphs. So I will start with an incident or story from my village. Somehow this was not working. Okay, sorry. So yeah, there was an interesting time around 1994 in my village when people used to get water from wells. Unfortunately, in the summer of same year, the water level went down, and we had to go to ponds and lakes to bring water even for drinking. So in the next year, the government of the village, which we called municipality/panchayat, they decided to install some T-wells to mitigate this water crisis. And then this decision has to be made based on a couple of things, actually 3 things, because we didn't have enough budget to install these T-wells at every house. So this decision has to be made on whether the government can access the land. Second is how the population distribution was across the village. And third is the road network, because people still used to have their bikes to get water from these T-wells. So based on these 3, you can see that they did a pretty decent job. So this is a partial picture of my village, and the red marks are the installed T-wells. So what's the point? The point is science is for everyone, not just big techs. And I'm going to show you very similar optimization problems which involve network as well as other type of data throughout this talk. So this talk will be based on 3 components. So in the first components, I will talk about optimization problems. So they involve network optimization. So the problems have the following form: that given a network, you want to make some changes in the network so that you can actually optimize certain objective. I'll give an example soon. In the second one, that's where we'll make a philosophical shift to solve the similar problems by machine learning. And in the third one, we'll see how we can address more of real-world systems by the methods which are designed mainly in the first 2 components. So let's see some examples. So first one, network optimization. And you might be very familiar with traffic. I don't know how many of you are living in Chicago, downtown. But this is an example from Los Angeles. If you have been there, you might know how bad this is in LA. So how do we improve an existing infrastructure? So here the setting is the following. The network is road network, and we want to optimize it. We want to optimize it by making some changes. But of course, you have a budget, so you have given a cost, and you want to design some better paths, or maybe you want to widen the path, making new roads. Now, how do you improve this traffic congestion in those networks? So fundamental question is, given a budget, which nodes or edges you should modify or improve to improve the overall traffic flow? And I'll show you how to use network information as well as the traffic information to produce a better algorithm, which will give you some improvement over existing computers. The second one, also you might be very familiar because most of us are kind of using social networks every day, and we see advertisements every day. And there is this famous problem which was proposed around 2003. So the problem is that how do you maximize influence in the network? So let's say you have to spread a particular information over the network, but you want to give this information to a few number of nodes or a few number of seeds. And by giving that information, you want to spread maximally over the network. So there will be an influence component over people, and you want to use these influences to spread this particular information. But this problem is this problem is commutual problem as well as NP hard. That means you cannot really have a polynomial algorithm which will give you an optimal solution. And this has been studied over many years with some discrete optimization techniques. What I will show you that how to use machine learning to actually learn that algorithm which has been proposed in discrete settings or is more traditional settings. So in the third one, I will talk about applications, where the applications mainly come from computational science. An example is, an example is how to detect events in stock market when you are just looking at communications between hedge fund employees, or how to detect price movements in stock market when you are seeing some documents from companies such as earnings calls. And I'll show you how to use machine learning as well as graphs to address these problems. So far, I talked about 3 problems. One is optimization, the other one is learning, and the other one is applications from computational science. So these problems all are connected through graphs. We'll show you that how to use different methods to address these problems. Now the question is how to characterize, optimize, and learn from graphs to solve these problems. So let's see more concrete examples. So first one is network design or optimization. So what is network design optimization? As I was speaking that, oh, you have given an initial network, you want to do some changes, or you want to add or delete some nodes, and then you want to have an optimized network. But this optimization is based on certain objectives. So the objectives could be based on robustness of network, or you want to improve some centralities in some nodes, or you can even think of some process like diffusion process or opinion propagation process. How do you improve them when you have some mechanisms such as modifying attributes or adding or deleting nodes or edges? What is the catch in these problems? These problems are design problems. I'm calling them design problems. It's mostly optimization problems. They are usually harder than their search counterparts. So what I mean by that, harder mean I'm speaking in technical terms. So it's basically in terms of NP hardness. So if you think of shortest paths, finding shortest paths are polynomial time. So you can find shortest path between a point A to point B in polynomial time. But if I change the problem to give you certain budget to improve in the network so that your shortest path gets improved or optimized, that problem becomes NP hard. So that's the main catch in network design problems. And the obvious reason of this hardness, which comes from the combinatorial effect, because you need to choose, let's say, k edges among m possible edges. So first one is how to identify key nodes to upgrade to traffic flow improvement. So what is the setting? The setting is you have given a traffic network. So you have source destination pairs and you know their popularity, how many people actually take this source destination. And you want to optimize the network to reduce commute time of people. And if you use some algorithms from literature, it shows that you only get a minimum improvement or not significant improvement. So I'm showing you in the figure, I'm showing you number of pairs in the y-axis, and x-axis has improvement. And you can see that only a few number of pairs or a few percentage of pairs only getting a high improvement. So what is the point of that? Let's say if you are taking an 1 hour commute and you only get 1 minute improvement, so your commute time becomes 59 minutes, it doesn't really matter to you. So we want to have significant improvement in your commute time. So the optimization problem is that maximize the sum of flows, or you can think of number of people associated with significantly improved pairs after reducing some delays in some nodes. So this problem is hard. I mean, NP hard, you cannot solve this in polynomial time. So what you can do? How can you design an optimal solution? So you can use mixed integer programming solvers to solve this, but you have to still, there is some complications, how to design or how to set up this MIP formulation. And what we have found is that even if you go to node version or edge version, they are basically equivalent. So this is very useful to have an MIP formulation. What's the catch? The catch is usually these MIP solvers don't scale. So the question is, can we design a simpler algorithm which might scale? So we are using greedy algorithm. So what is this greedy algorithm? You can choose your node to improve or edge to improve in each step. So let's say if you have to choose k nodes to improve, you can choose one node without knowing what the other k-1 nodes will be. Then you can pick your best node. In the next iteration, you can pick the second best one. But the problem is that greedy, the good thing is that greedy is almost matching the optimal solution. So that's good news, because you had this really complicated MIP formulation, which is hard to scale, but then you have much simpler version, which is actually matching your results from MIP. The problem is greedy is also computationally expensive, because once you choose a node to improve, you have to basically go and improve all the shortest paths and see how many of them actually have been improved or have been affected because you improved certain nodes or certain edges. So what can we do? Can we kind of mitigate this? Can we look into the data and solve this problem? So let's look into the data and then see what data tells us. Sorry, there's a delay of me clicking this button and the slide progressing. Let's see. Okay. Yeah. So what we'll do is we'll do importance sampling. So what I'm showing you in the figure is data from 3 different cities. So one city is Beijing, the other one is New York, the other in San Francisco. These are cab trajectories. And you can see most of the pairs are not that informative. So the flows are concentrated in some pairs. So what we can do is we can use this knowledge to build the algorithm. So what we did, we kind of sample in based on their importance. So we sampled a few pairs and just solved our problem on those few pairs, and that can reduce your computational complexity by a lot. But the question is how good this is in terms of quality, right? Because you're going to sampling. So are we getting as good a result as greedy or not? So we are showing that you can actually reduce this error or bound this error with high probability. So n is here number of nodes, but using only a few samples. So samples are also only in terms of logarithm number of nodes, but then you have some constant based on number of flows. Sorry. So the constant based number of flows. So then we are seeing that, okay, this you can qualitatively, you can guarantee that your importance sampling will give certain bounds of error. But does it work in practice? So it seems like it does. So for the first figure, I'm showing you flow quality result. And the second figure, I'm showing you the time results. So first figure tells you that the green curve, which is our algorithm, is kind of close to the red one, which is greedy. What the second curve tells you that our algorithm is much, much faster, while being also good in quality with respect to the computers. So this is all good news, right? Because first we saw that we can have an MIP formulation, which is complicated. We can have a greedy algorithm, which is much simpler, but it's hard to scale. But then we have much simpler algorithm, which is based on sampling and can scale. So here I'm showing you results based on only 60K nodes. When you go to 1 million node, greedy doesn't scale even. So you have to wait probably for 2 to 3 days to get the results. So in this area of work, we have seen several problems. So I just gave you an example of infrastructure improvement, but you can also think about network robustness, how to judge network robustness when you modify the network, or how can you do manipulation in networks? How can you increase balance, which is very common in social science? How can you do balance in social network? How can you mitigate fake news or spread of fake news social networks? But these problems, they need, because of the problem structure, you need different algorithms to address them. One thing we have found, all these problems actually lie in different spectrum of hardness. So for some problems, we achieved approximation within constant factor. For some other problems, we couldn't. So what we did well in these algorithms, we came up with fast algorithms, which also had theoretical guarantees. But what is missing here? I mean, this is very crucial. So let's criticize all these methods so that I can go to the next one and can kind of come up with some exciting techniques to address them. So the missing part is the algorithm part, right? So basically, let's say I was giving an example of Chicago traffic data. So you have really nice algorithm to solve this problem. So you have given Chicago data, I give you my algorithm, you apply them, you get a result. But when you change the Chicago traffic to some other traffic, let's say New York traffic, you have to again employ your algorithm, right, to get the result. So whenever you are changing your instance of the problems, the algorithm has to be applied again, and you have to get the results again. What is missing here? We are not really using the knowledge from the previous solutions, right? So the solutions might have a pattern which your algorithm already tells you, but we are not using it. We are using the algorithm from scratch again. So maybe you can get a sense where I'm moving towards. So again, sorry. Yeah, so I'm moving towards that. Can we use supervised learning approaches to design even better algorithms? So I'll talk about it more. So the next one is machine learning on graphs, especially to solve such combinatorial problems, which I was giving an example of. So before going to machine learning, just to give a primer on graph neural nets, because I'll be using it to design some algorithms. So graph neural nets are a generalized version of deep learning, especially on graphs. What it does is it takes a node as a graph as an input and kind of creates a low embedding space for all the nodes and sometimes graphs, depending on the problem. This is being very effective for several problems, especially on node classification, link predictions. This goes also beyond the graph space. You can use it in NLP, you can use it in computer vision. The idea is simple. The idea is if you want to tell something about yourself where you are a node, then just look at the neighbors. And then how you aggregate information from the neighbors, what you call as neighbors, that depends on different mechanism. And how you aggregate them, that also depends on your machine learning architecture or / deep learning architecture. So the idea is actually, idea is from previous work for many years. So the idea is not novel, but how do you aggregate them? That kind of changes. So what our claim is that GNNs are awesome, but it won't be sufficient to solve combinatorial problems. We'll see soon. So then again, going back to how to learn algorithms for graph combinatorial problems. Do you have any question at this moment? Okay. So what's the motivation? As I was speaking, that we are solving same problem with slightly different data. So for example, I was giving influence maximization problem where your social network doesn't change much, but you may need to do averagement every day, every other day, or maybe multiple times on a day. So the setting is the following, that you have a problem and you are giving a graph combinatorial algorithm, which is on more of traditional sense. This could be greedy, this could be based on sampling. And then you have several instances and you are generating several solutions. So can you use this knowledge? Can you use these instances? Can you use this solution and try to learn what was the pattern inside the algorithm which gave such solutions? So the question is, can we give this to a machine learning framework and even better, even design better algorithms? So here's the problem setting. So you have given an optimization problem I that is defined, and your distribution of problem instances are also defined. So because you want to generalize your machine learning algorithm on unseen instances where the instance is a graph, but it has to come from similar distribution, then otherwise you will have distribution shift and you might be not able to generalize that well. So what are the promises? The promises are that we will be able to solve NP-hard problems more effectively. And the second promise is maybe if you design it more intelligently, it can actually learn on small graphs, and then you will be able to generalize on much larger one. Also, what's the hope? The hope is that it can actually mimic what the discrete algorithm, the conventional algorithm was doing. And we'll of course solve these problems, solve these more popular problems on graphs. But there are many challenges. Yeah, so the challenges are, so one is you need to generate training data, but you have to appreciate like how hard it is, because we are trying to solve an NP-hard problem. So that means whatever supervised algorithm, whatever traditional algorithm are using, it cannot be optimal. So you have to use a suboptimal algorithm to design your training data. So you need instances, you need solution sets given an algorithm. Second is, I was talking about generalizing on much bigger data. So if you remember how I was setting up my influence maximization problem, that has a budget. So you need to choose k number of seeds to give your information to. But if you train on small data, then you of course have a small budget. You need to, when you go for a larger data, you will have a larger budget. So you need to also generalize this, you need a generalization on larger budget. Third is your machine learning framework inference at least should be very fast. Otherwise, there is no point of designing a different algorithm, even more sophisticated ones, which is taking a lot of effort. So let's see if we can mitigate these challenges or not. So first one is data generation. So here we are using probabilistic greedy to generate answer sets. Why is that? So there is a catch, because the problem I took is the problem has a very nice property, which is called submodular property. So if you have submodular property, you use greedy algorithm, it at least guarantees within some constant factor of optimal solutions. So that means greedy could be a good algorithm for supervision. But we're using probabilistic greedy. Why? Because once you apply greedy algorithm, it will give you a particular set. But if you will apply multiple times in a more probabilistic fashion, it will give you multiple sets. So you would know which nodes might be included in your solution set. The second part is we are filtering by applying graph neural nets. So we are filtering candidates. So let's say for you are going to improve 100 edges within a million number of edges. So here what we are doing is we are just predicting which edges might be in your solution. So in the end, you might end up by applying this lightweight version of graph neural nets. You might end up only seeing 1,000 edges which might be relevant. But among those 1,000 edges, you still need to choose 100 edges. So there is still a combinatorial part which you need to solve. So for that, we use reinforcement learning. And I'm not going too much details. We mainly use Q-learning. You still need to set up your Markov decision process. You still need to set up your state action pace, how it will be, but I'll be happy to talk in more details. So apparently we solved all the challenges which we are talking about, but now is the kind of moment of truth, right? That whether it works in practice or not. If it works, it's good. If it doesn't, then maybe we have to go back home and think all these things through again. So let's see. So these are the results. So these results are very inspiring for us. What we are showing you is data which has a large number of nodes, 1 million nodes in all the data sets. You are seeing in first two columns time. So IMM here is the most valuable algorithm, especially to solve influence maximization problem. So in more traditional sense. And then what we are seeing is that our influence spread by our algorithm and IMM are almost similar. So that's good. That means we can do qualitatively as good as the traditional algorithm. But what about time? In time, we are much faster. So that means it was worthy to actually go through the machine learning version, try to learn the pattern of the algorithms and apply them on bigger data. So these results were really inspiring for us. And we went to solve more combinatorial problems by seeing these results. And even this was the first neural approach to solve influence maximization problem. But there are few catches here. So one is, if you remember, I chose a problem which has a nice structure, submodularity, so you can actually get nice supervision. Also, the problems I was talking about has budget. So these are budget constant for a problem, right? And not all the combinatorial problems will be budget constant. So let's see if we can drop those assumptions and can do similar machine learning based methods on other combinatorial problems. So we'll try to solve how to learn graph and subgraph similarity. So when I talk about graph and subgraph similarity, the similarity of objects come into your mind. So I'll give a very simple example. So images, right? So you take images and then you try to compare how you were when you were like much younger age. And then this comparison is kind of inherent in our mind. We also take our iPhones or whatever phone you have and then check images, try to match the similarity between two objects. But what our goal is to see similarity on objects when the objects are graph. So if you represent your image by a graph, if you represent your text by a graph, then this object similarity between graphs come into your hand. So an example is graph querying, which is a common example. You want to, so if you have database of chemical compounds and I give you certain structure, and then you want to find if the structure exists in the database or not. This is popular problem in graph mining. Can we solve this problem through machine learning? So just to set up the problem, the setup problem is, like I was talking about, that subgraph similarity is a fundamental task in graph mining. It has also applications in computer vision, especially as graph is used in scene generation a lot. But most of the graph similarity problems are being solved again with some solver, which doesn't scale. So I'll give an example of two graphs. So I'm talking about query because I was talking about graph querying problems. So query is one graph and you have target graph. So let's say if you want to find similarity between these two, you can. So we are talking about how much minimal changes you need to make to the query graph so that it turns to target graph. So for example, in the second figure, you are seeing that if you turn the blue node to a red one, and then you add an edge with the green one, then your changes are perfect. So basically the distance between these two are 3. You have to make 3 changes to make the query graph to the target graph. That's graph similarity. So we are talking about a certain kind of graph similarity, which is graph edit distance. You can also think of the same problem in a subgraph setting. So in subgraph setting, you have to just look at the subgraph. So if you make the blue node to the red node and you are done, so subgraph similarity is 1. Unfortunately, computing both subgraph edit distance and graph edit distance are NP hard. So you have to solve these problems, but you can see, right? There is no budget constraint here, and there is no even the problems and the objective is not submodular. So you have to design a kind of different kind of architecture for this. So this is our architecture, and as I was saying about training data, generic training data is really hard for these problems. So what we did is we came up with a Siamese architecture, which uses parameter sharing so that you don't need to use a lot of training data. Also, second quality of this is pair independent embedding. Why this is important? Because I was talking about this graph querying problem. So you have a database of graphs. If you have pair independent embeddings, then basically you can embed those graphs which are in the database in a pre-training fashion. So you embed them once your query graph comes, you embed them and you kind of check their embeddings to find the similarity. Third is the function f. So even the problem is different. The problem has certain structures. So basically GD is metric and ACD subgraph distance has triangular property. You still need to make those properties preserved in your embedding space when you are embedding the graphs. So that's what our architecture does, and the literature cannot preserve these properties. So quantitatively, we are preserving some properties from the problem. And this is, sorry. So yeah, if you want to open the GNN layers, so it's basically their main 2 components. Well, you are capturing the structure by using some GNN layers, and then you have to aggregate somehow those embeddings through some aggregation function. We are using the sum pool here. I'll be happy to talk about this architecture in more details if you're interested later after this talk. So what we achieved really good performance. So if you see the left-hand side figure, I'm showing you query size in y-axis and ACD values, subgraph edit distance values in the x-axis. And so the deeper the colors are, it's doing more mistakes. So if you compare ours versus another neural approach to solve the same problem, you are seeing the neural approach doing more mistakes. In more quantitative fashion, we are producing 2 times lower RMSE. The good news is our method can do ranking. So I was talking about querying, right? And then here the query is this particular graph, and then our method ranked the other graphs as rank 1 and rank 2. Apparently, it seems that there is no really match between query and rank 1, rank 2 graphs. But if you look at carefully, basically they have subgraph edit distance of 0. So that means our method also can perform ranking. So this is good news because now we have methods mostly based on machine learning which can go beyond budget constraint problems. And this is also inspiring. We can solve maybe more complicated combinatorial problems in hand through this kind of approaches. So now let's look at a different kind of problem. So this is also combinatorial problem, but the flavor is different. So in any machine learning algorithm, the question comes why we should kind of judge the robustness of the algorithm. Why is that? Because of this, right? So basically, there is this famous example from computer vision that so the image recognition algorithm was applied to this particular figure. This figure is a 3D printed turtle, and unfortunately, the algorithm detected is as a rifle. So that means your data can go really wrong if you are not careful, or your algorithm can go really wrong because of some little variation in the data. And this is true for graphs as well. So in graphs, I was talking about graph neural nets, which is a message passing algorithm. You are getting your messages from the neighbors, and it also depends on how you aggregate the information from the neighbors. But this is also vulnerable. So if you take a look in the figures, so the left-hand figure is a clean graph. So you want to predict a level on the node, and then clean graph maybe gives you 7 as green. But when you perturb a little bit, because its neighborhood changes, it might give you a different solution. And wherever you use, GNNs, like for product recommendations, for other social friend recommendations, it can go really wrong if your data is a little bit perturbed. So what we did, we wanted to check vulnerability in GNNs. But there are different philosophies how you can attack. So mostly if you know all the information about your model, then it's mostly white box attack. But then your attacker is more powerful, right? It has more knowledge. So what we wanted to do is to make many things unknown to the attacker. For example, one is the model, the neural architecture which you're using, also the task, what kind of task you're performing. Then if these two are unknown, can we still do the attack on graph neural nets? That would mean that even without limited information, an attacker can do several damage to your graph neural architecture. So only thing known is the network structure and the embeddings, the representations of the network or nodes. So the idea is very simple. The idea is because when you go to the embedded space, you also look at the neighborhood. So let's make the neighborhood distorted. So make changes in the graph in a way so that you can maximally distort your embedding. So that was basically our objective. And I'm not going into too much details into the architecture, but the architecture was assuming that you can add or delete edges in the graphs, and we have to use some proxy model. So we use graph isomorphism network, which was a good proxy for all the GNN models. And if the method was also effective and efficient, we'll see in the results. So here I'm showing you results based on drop-in accuracy. So the task was not assumed, right, in our model. So you can do in different tasks. One is node classification, classical task, and link prediction. And what you are seeing is through our attack, the drop-in accuracy is much higher. So TANDIS is our method. And if you compare with some baseline methods, our method is outperforming them on several architectures as well. So GCN is a particular kind of architecture, GNN architecture, GAT is a different kind. So the implications are that you can still do attacks without knowing much information about the model. What's the good news? The good news is if you know the vulnerabilities, maybe you will be able to build better algorithms to guard or to protect those kind of GNN models. So now I'll talk more about the application part. Do you have any question at this point? Okay, so let's go and see some applications.
I have a question.
Yes.
So, one way to try to tell about so all very much. There is another way you can try to by actually what information I'll give an example of the one looking at actually X-rays of
Mhm.
and what the algorithm
Mhm.
one hospital has a lot of image, some control play, and see if the model is not running or not.
Mhm. Yeah.
Also,
Yeah. No. Yeah. So this is a valid point, and you just talked about a particular area of research. So people are a lot of people are working on interpretability of GNNs, and these two differ. So I'll just give an example of how these two differs in philosophy. So interpretability is you are looking at a part of the data which is more relevant to your result, what you got. That's how you're understanding the model. And the robustness is a little bit different, because in robustness you basically trying to see how your model is well equipped when your data changes a little bit. So there are two different philosophies, but lots of work is going on. We are also doing some work. I will talk about it a little bit in our futures agenda. And thank you for the question. Okay, so let's see some applications. So here I'll talk a little bit about event detection. And event detection might be very familiar to you. So here I'm showing you three different figures with three very different titles. So first one, I'm showing you a traffic network, but I'm talking about event in a city. And the second one, some employees are saying something. So basically I'm showing you communication between employees, but the title is events in stock market. The third one, I'm showing you a bunch of tweets, but I'm talking about extreme weather. So the goal of the project is this: whether you can predict an external event by seeing some network associated with the process. So these three examples, right? And so you want to detect a sports event in the city by seeing the traffic information in the city, or you want to do some price movement in the stock market by seeing communication network between hedge fund employees. So this is the question: how to detect an event from evolving patterns in the graphs. So also in terms of graph neural nets or representing graphs, in dynamic graphs, the philosophy changes. So the usual way is you get some embeddings by pulling the features, and then you do graph embeddings from those node embeddings, and then you do some predictions on top of the graph embedding. But one version is micro, the other version is macro. So in the microdynamics, you basically see how these representations of the nodes changes over time, and then you're trying to predict something about the event. In the macro one, you want to see how the graph embeddings changed, how the embeddings of dynamics of the embeddings of graphs are. So what we are seeing is, for this kind of events I just talked about, the macro dynamics are more relevant. So we used macrodynamics and GNNs and some attention network to solve these problems. And in the literature, they mainly talk about the microdynamics one. And here you can see that for the event detection problem in this kind of events, actually the macrodynamics help. They outperform the baselines. And not only that, we can even do event diagnosis. So this is an example of the traffic network, the traffic dynamic network only in 2D. But you can clearly see whenever there was a game on Yankees or Mets, they're having a very different representations on the space. Not only that, even the game types are being clustered. So that means this is learning something specifically to the graph structure, which is helping in the representations part. Next, I'll give you an example which is more familiar. So patent review systems, I am sure that you guys are very familiar with patents. So what happens with patents are, patents reviews are very similar to paper reviews. So in paper reviews, you submit papers in journals, and then you get some reviews, you rebut them, then you submit again, you get an acceptance and rejection decisions. In patent reviews, it's the same. You apply for, you file your patent application, it goes to an expert who can review your patent application and gives you a bunch of comments, and then you take these comments, you can revise them and submit it again. What's the difference? The difference is you need to pay money each time you file, and it has been shown that each patent application takes a huge amount of money, almost in terms of $10,000 on average to file and to get submit and resubmit. So the question is, can we improve this review system or not? So here we are showing you the data from US patent application system, which was 4 million applications. Some of them are granted, some of them are rejected, and some are still pending. Yeah. So patent system is
Sorry, is that just US?
This is US data, but in our work, we're using data from Canada patent system and also as well as UK. So these results, actually, our model results, they are consistent over all these 3 data sets, but this is only for US. So the goal is this, the goal is, can we improve the system? Can we tell something beforehand to the applications which are filing, even to the examiner, whether these applications are good or bad? So one part of the problem. So what we are seeing is, by our method, we are getting really high accuracy, especially when the model is really confident. So in y-axis, you are seeing the top precision scores. In the x-axis, you are showing the model's confidence. So that means our model is doing a pretty good job in terms of finding which applications are good or bad. Not only that, we can not only that, we can even do several things with that. We can even predict which parents will be highly impactful. So that means it will get more citations. In these models, we have also done some analysis on what are the things they are learning. It also matches what the experts would say based on those parents. The implications are clear, right? That it improves the real system. And if we can actually have a trusted model, then it might save a lot of resources. So at this point, if you don't buy this problem, basically there's a company which is trying to do the same and making probably a lot of money. And whereas we are, of course, we are doing science and contributing to science. So let's see one more example. So the question is, how do you detect stock movements from earnings calls? I'm not sure if you're familiar with the earnings calls. This happens in each quarter from companies. Companies talk about the company's health. What are the plans about these companies? And then people kind of react to it, right? People either buy the stocks or sell the stocks. And because of that, price movements, like price has some movements. So I'm showing an example from Tesla in 2019. I know you would argue that it's a very different scenario from 2020, but let's not go into that. So just let's focus on the price movements example. And Tesla stock price, whenever the earnings call happened, the price moved. So the question is, are the earnings call important? So from this figure, it gives a sense that it is important, but actually they are important from even more evidence. So over the years, the CEOs or the company board who are actually creating these earnings calls, they are being more positive, which makes sense, right? Even if the price goes up or down. So our objective is, how do these calls affect prices? We need to formally we need to study this in more systematic way, how to quantify these effects. And sometimes we think that, oh, look at just some hard data. Look at data such as whether the earnings calls beat the sales or not, whether it actually beats the expected earnings per share or not. Can you get some signals from the earnings calls itself, even better than this hard data? So here I am showing some results from the hard data, which you might expect to be really good. But unfortunately, if you make only those hard data as your predictor, it is not doing well. So in the figure, I'm showing you on the y-axis beat by miss fraction. So essentially what you should see is, you should see only upward green, because then your price actually moved upwards whenever it has a positive effect. And you should only see downward red, but of course, which is not happening. That means you cannot really trust on hard data. But can your earnings call be a better predictor than that? So we are seeing actually it can. So our models included GNNs on these earnings calls and provided a better prediction. We are seeing average recall and average positions for these price movements. And we had very different ways of definitions, how we call these price movements up and down. So the clear thing is that the semantic features from the transcripts are more like better predictor than the hard data. So what does it tell us? It tells us that we can actually help in a deeper understanding of the market for everyone, and maybe how people are kind of spending time on earnings calls. We have a good way to learn what are people saying in these earnings calls. So these are the things. Now I'll talk a little bit about future agenda. Do you have any question at this point?
Sourav?
Yes.
2 questions on the stock market. You had language on your last slide. I can't recall the exact words, but you had the GNNs and the
Language models?
Language models.
Mhm.
Could you talk a little bit more about the language models? And a second question is, have you considered layering in addition to text analytics, audio, right? Because if there's a difference in the way that people are communicating things from an audio perspective, would that potentially add another layer of interest to the research?
Yeah, these are very good points. So first question is, so the language models, there are a lot of progress on language models. You can pre-train them, and then whenever you have a different domain, you can go to the domain and use those pre-trained models to use for your predictions. Here, the problem is when the domain changes, the language, how you speak the words, especially. So for example, the patent domain is very different than earnings calls domain. So you need, maybe the pre-trained language models won't be enough for that. So that's why we used a graph neural network-based model where the graphs were created from the document itself. And then we also used unsupervised language models, which was giving a different perspective of the domain itself. For the second one, second question was that whether
Just using this so the people online can hear.
yeah, sure.
The second one's related to layering in
Audio.
not just the transcript, but the audio to the earnings calls research.
Yeah, this is definitely a good suggestion. We didn't do that, but this will be probably a future version of this work where you can actually incorporate the audio version. You can see the emotions. We just use the emotions from the text, but this is definitely a very good suggestion. Thank you.
So what you really want is the market react to the real information, the hard data, right? You actually don't want it follow the earning call. So this is like basically saying people are not doing decision wisely.
No, what we are saying is that we don't understand how people react on certain things. So basically, when the earnings calls come, the usual thing we think that, okay, people might look at some hard data and make decisions, which is certainly not the case here. So that means that people actually interpret this soft data, like which is written in the earnings calls, how they kind of interpret is a little bit different than the more conventional thoughts that they would do.
Yeah, I see this point, but I mean, you want people react to the data that was not biased and not so mislead.
I mean, I don't understand this point because I don't need it. I don't want anything, right? I just want to understand how people react. But it's second question is like the bias is a very generic term. Like when you say bias in the hard data or you say bias in the text. So what I understand from your question is you're talking about people who are actually writing these earnings calls. They might be really biased. They might be positive about the earnings calls. And then people might get distracted by their optimism in the earnings calls, and they can manipulate that.
So you see the earning calls, the sentiment is simply go up.
Right.
So apparently the company know that you got to face in a way that people don't fake out or don't pull the triggers.
Right.
Pull the plug.
Yeah,
but they should pull the plug if you are really performing bad.
Yeah, so there are two answers to that. One is you saw that how even when the stock went down, they were actually positive. So despite of them being positive, the stock went down, right? So this is one. Second is that means that the consumers who are actually reading them, they are going beyond how much optimistic you are. Second question is, I don't think the company's board will show some fake optimism because that also hurts the reputation of the company. So there will be a sweet point. But this is a great point that like whether actually CEOs can or company board can manipulate the earnings calls optimally or not to kind of make their values up, and that is still in question. And how do we mitigate that as consumers, right? This is a great point. Thank you. Okay, so any other thing? Okay, I'll quickly talk about future agenda. It seems we don't have much time. So what is, as already Professor Amaral did my job. So we are talking about a lot of interpretability in this kind of methods. So as we learned commutative algorithms in our undergraduate computer science courses, right? That we know each step, but from black box model, for neural models, we don't know so much. And the most of the work is going on towards mostly node classification and link predictions. So we want to understand these methods even in stepwise fashion for commutative problems. So we are doing some work around that. We are doing some counterfactual generations for graph neural network, like what counterfactuals actually make these GNNs behave in a different way. Second, I was talking about event predictions. So you can think of this interpretability based on the specific task. So let's say if we have a particular event, then a certain parts of the graph is being very active to predict that event. When the events change, whether the different part of the graph is being active or not. So this will also improve our understanding for this ML methods on graphs. Second is the main objective, that you have to solve many other commutative problems, and not all the graph computers have same complexity. So we are trying to think of combining all the research that has been done in network science, as well as combining it with neural approaches, whether we can do better job and designing better algorithms. So we are also doing some work in this. So one is neural graph partitioning. So if you remember your divide and conquer algorithms, so if we have a neural graph partitioning scheme, it might help overall in your all those algorithms which actually use divide and conquer. Second is, I was talking about how hard it is to generate training data. So if you do multitask learning, the goal is that you can generate data for an easier problem, and you can use this for much harder problem. We are trying to mitigate that. Hopefully it will improve. Hopefully it will improve like a lot of research in graph algorithms which are already existing. We also think of how these network optimization techniques are being useful in mostly for social good, for disaster response. Here I'm showing you on a map from Senegal. So these red things mean they have this blockage while during flood. So can you actually minimize the number of incomplete trips via network optimization or not? We're also doing some work on sustainability and as well as in healthcare. So the first figure is showing how to predict ground level ozone from data from Taiwan. And you are seeing that our predictions is almost being accurate through the actual observed values. We're also thinking of how to control diffusion, misinformation in the network through network design. So if you all remember, like we have recently gone through a pandemic, and the mechanism there was to isolate people. That's basically network design. You put a person and then you cut off all the edges. So we are still thinking how to include this network optimization techniques for better algorithms, especially in healthcare. I just talked about parent application system and earnings calls. The main goal is to understand how review system works in different domain. So one domain is parent applications. We also talked about the consumer reviewing on earnings calls. And the third is the grant proposal. Like you apply for grants, like all the profs do, and then you get some decisions on the grants. So how the decisions kind of affect to write the grants better or not. So the challenges are many. You need domain knowledge, you need domain expert. Also often it lacks good data. We are making some effort to collect data sets from companies. Also, Northwestern was very generous to give us grant proposal data set so that we could work on these problems. And in a way, this will actually help in faster innovation system and better decision making. But the social systems has a problem. So it could be biased, as he was mentioning in earnings calls, that the company owners might be really biased. Which we are seeing in parent review system is that review systems is biased towards certain kind of gender, especially in acceptance of applications. So in x-axis, we are showing the year, y-axis showing is percentage of acceptance rate. For male and female, there are different acceptance rates. So we're also working on how to mitigate or how to find these biases in real systems. We're also working on some algorithmic fairness, where the fairness is in terms of merit or in terms of individual perspective. And hopefully these theories could be helpful in actually mitigate these biases in real world systems. So this will be more of correcting real system than improving it. So let me show my gratitude to all these people, because these works have been done in teams, and it won't be possible without them. So I'm really thankful for them. So what this talk was about? This talk was about mainly three things. One was network optimization. The other one was how can you use machine learning to solve same combinatorial problems. Third was more of application. So you can take three things. Probably have seen various applications in graph problems, even beyond computer science, which has applications in business and law. Second is you saw some theoretically grounded algorithms, which are more of convolutional techniques and use solve combinatorial problems on graphs. Third, you have seen how we can actually apply machine learning to learn these algorithms. In future agenda, there are mainly two parts. One is the fundamental part, the interpretability part, and making efficient algorithms. In the application part, we are trying to do apply problems in social good, also problems in social systems, which have implications on other disciplines as well. So before I finish, one last thing. Yeah. So hopefully you know Professor Banerjee and Professor Duflo. They are doing great work in economics. They have also recently won Nobel Prize, and they have done a tremendous amount of work, especially to improve lives of poor people. So they are inspiring a new generation of researchers. So hopefully with these inspirations, with all the future skills, promises, methods, we'll be replicating something such as this. Sorry. Something such as good data science for hard times for the people who need it most, such as people in my village. Thank you.
Thank you. Thank you, Sourav. Great conversation, great research. One question came in online, back to your stock market research. I'll take a moment to answer that if you don't mind. Regarding earnings per share, what is the baseline comparison? And our analysts' prior guidance accounted for?
For earnings per share, we are just looking at whether the earnings actually beat or miss the expected earnings per share. And we also use hard data for sales. So what is the expected sale, whether this actual sale actually beat or misses the expected sales or not. And these are mostly comes from analysts. These numbers are usually comes from analysts. So when we do compare, we compare with same machine learning method. So these values are used as features. And in the other hand, also the semantic features from the transcripts are being used as features. And then you use the same machine learning model to predict these two. So the hard data are basically being used as a baseline.
Thank you. Thank you. Are there any more questions here from the group? No?
Yeah.
Developing a bunch of new cool techniques, but I think sometimes with the cool new techniques, we forget about the usefulness of some other approaches. And so when I was thinking about the example, for instance, just the stock market, because a lot of people have been asking about that one stuff. So when you use a model like this with deep learning, you assume that you don't know anything about the system. Because essentially what you are doing is you are saying, I'm going to consider these variables and this is what these features, and that's what I'm going to use to learn and make predictions. But for instance, we know that there are differences in how analysts follow companies, if they are in tech or not. So industry would be something that it could be important for how things are interpreted. Age of the company could be important, right? Because if you are in a early stage growth, losing money is not a problem. If you are GE, losing money is bad. Or who the CEO is, right? I mean, there are all of these people that just love to kiss Elon Musk's ass. And so, you know, it's like he could be saying blah, 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 and people, oh, he's a genius. So the Tesla's price should go up. So there are ways in which, you know, some features are like to be important, and I think that when you have that situation, it's probably a good idea to kind of use sort of a mixed approach in which you try to account for the things that you know that should be or could be important, and then see how much else is explained by the new method. Because I think one of the dangers is that you put everything in the black box, and then it's very hard to say what is going on in here, right? I mean, it's very nice that you went and looked at the stuff with the gender in acceptance rate, right? Because that's demonstrating something. And, you know, the models could be learning some of that from the language, right? They can understand, okay, that idiot is Musk, so I should give him a benefit. The model will learn that, but you don't know why. But you actually have said, this is about the CEO, and there is a parameter that relates to each one of the CEOs and how much effect each CEO has. Then you are learning more in a sense than the other way. So, I mean, the techniques are really, really cool, and you have done such a great amount of work. I'm just thinking that it's dangerous not to keep using what we have learned that is useful and not start from scratch.
Yeah, this is a very good point, because this gives me a chance to answer the question as well. So the thing is, in this work has been published recently in www community, and we have actually seen and like this control on the CEOs, control the gender of the CEOs, and what the sectors the companies are, because some sectors are different. So all these values has been taken care of, what you mentioned. But good thing which we didn't take care of is what actually machine learns, or if the machine can learn the types of those things or not. And this is somewhat more, again, going back to the interpretability part, that whether we can actually we can say something about, let's say, what are the things which are essential to the domain, and that could be learned by machine or not. So this part is still explorative. But thanks for the question. In the paper, we did the regression model where we control for all these variables and show some results. Yeah, thank you.
We'll wrap up our session. Thank you very much, Sourav. Wonderful presentation. And please join us next week. We will be hosting Anjali Bhatt from Harvard and the Santa Fe Institute. She will be sharing her research on organizational merger. So please join us then. Thank you.